Okay, let's get started, I guess. I'm going to talk about my thesis, fault recovering garbage collection of actors. And before I get into these actors, I want to talk about the distributed resource management, a broader problem. And so distributed systems, they manage these scarce resources like containers and memory and disk space and so on. And programmers need to write code that reclaims those resources, but this code can introduce new bugs. So if you reclaim memory too early, you get something like a seg fault. And if you reclaim memory too late, then you get a memory leak. So it's a delicate balance that we need to strike here. And here's a particular example from Hadoop that I found in a bug database. In Hadoop, you've got this, oh wait, I see that Indy's raised his hand. Do you want to go ahead? Oh, I have to ask you to unmute.
I would request that participants be allowed to unmute themselves at will. It's very unusual for the host in a defense to have unmuting powers. So I believe all the participants should be allowed to unmute themselves whenever. For me as a committee member, it's very hard to wait for the host. I should be able to ask a question at any point of time.
Okay, sounds good. I thought I had managed to give you guys permission to do that.
No,
but
I can't. I couldn't unmute myself just now. So
okay, thanks for raising that. Okay, so I should have fixed that now, and let me know if that's still a problem.
Thank you.
So back to this example, we've got this Hadoop example where in Hadoop you used to have this job tracker which supervised a task tracker which supervised a task in progress. These are all processes. And what would happen is if the job tracker crashed, the task tracker detected that failure and it would initiate this cleanup process, and eventually the job tracker would send a reinitialization message. But the bug was that if the job tracker rebooted too quickly, the task tracker would try and reinitialize and clean up at the same time. And so this was a race condition that caused a bug. This is an example where resource management introduces a new bug. And so we're going to study this resource management problem in the context of the actor model. That's a model where you have these processes called actors that are communicating by asynchronous message passing. And what we want in this model is an actor garbage collector, actor GC, which is a middleware that detects these useless or garbage actors and it kills them for us. This is a problem that's been studied for more than 30 years, but surprisingly, the most popular actor frameworks like Akka and Airline, they still don't have actor GC. So this is kind of a question of why would this be the case? I raised two possibilities. One is that previous actor GCs impose some performance overhead. Some of the GCs require something like a causal message delivery or locks or memory barriers, and this might be a problem that you don't want to introduce into an existing system. And the other, perhaps more important case, though, is that previous actor GCs aren't fault recovering. And what I mean by that is that if a node crashes and it held on to some distributed actors on some other nodes, those actors will never be garbage collected. Those resources will never be collected. So that example that I gave you before in Hadoop, the existing actor GCs aren't able to deal with that kind of problem. And because of that, programmers are kind of left, they still have to write this manual resource management logic if they want to be able to handle failures. So this is something that we'd really like in actor GC is something that's fault recovering. So in this talk, I'm going to talk about why is actor GC so hard? What's the challenge here? And I'm going to introduce my new approach, which is a collage-based approach. I'll explain what that means. And I'll show how I use that approach to develop what I believe to be a practical implementation in Akka that is fault recovering. It's capable of reclaiming those resources that were held onto by crash nodes. So before I start getting into that, I should give an overview of how actors work, particularly in the Akka actor framework. In the Akka actor framework, you've got these cluster, which consists of nodes. Here we have 3 nodes. And nodes contain these actors. Here's actor A. And an actor executes some code called its behavior. Here, actor A is executing behavior foo, and the behavior will contain some fields, some local memory. It'll have a constructor that runs when it starts up, and it has a message handler that says, when I get this message, I do X, Y, Z. That's what an actor looks like, how you program them. And actors can have 2 states. They can either be busy, which means that they're currently running and doing something, or they can be idle, which means that they're doing nothing and they're waiting for a message. These are key concepts to understand. And when an actor is busy, it can do the following things. It can perform effects like writing to a file or writing to a database. So these are things that are kind of observable, or printing, for example. And it can also spawn actors. Here we have this actor A is spawned actor B on the same node and actor C and D on these remote nodes. And these actors can then send messages to other actors. And here this actor A is sent M1 and M2. It doesn't really matter what the payload of these messages are. It could be some large data structure. It could be an integer. We don't really care about that. But what we do care about is if the message contains references. So actors can send messages. Here we have this message M3 that contains a reference to the actor D. And this reference, this reference will allow, when C receives the message, it will allow C to send messages to D. So this A has sent this message M3. But in order for an actor to actually receive a message, it can't receive a message while it's busy, while it's currently doing something. It needs to first become idle in order to receive the next message. So in this actor C, what it can do is finishes processing whatever it's processing, becomes idle, and now it's able to receive either M1 or M3. And it receives M3. Now it's got a reference to actor D, and now it can send messages to actor D. Now I want to stop for a moment, and you'll notice that the messages M1 and M3, they were delivered out of order. And in the actual Akka actor framework, it does provide certain guarantees about the order that messages are received in. But in my approach, we don't really need to make any assumptions about message ordering. So just for fun, I just had M3 delivered before M1 was delivered. So anyway, actor C over here now has a reference to actor D. It can send it a message like this. And the last thing I want to stress that busy actors can do is they can forget references as well. And the reason I want to stress this is that references are not acting like sockets or channels, right? Because even though C no longer has a reference to D, this message that it sent, M4, is still out for delivery. So that can still happen. So references are just kind of these addresses that are floating around the system. That you should think of them that way. So the key assumptions that make this, the actor model is that actors are message-driven, number one. And what I mean by that is that they can't spontaneously jump from the idle state to the busy state. If it's idle and waiting for messages, it needs to get a message in order to start being busy again. And those messages, they don't just appear out of thin air. Although in the thesis, I actually relaxed this a little bit to deal with timeouts and things like that. But in this particular talk, we can assume that if an actor receives a message, it's because another actor sent it a message. And the third assumption is that references also don't appear out of thin air. So actor D down there can't just get a reference to actor B. The only way it can get a reference is if it had spawned actor B, or if some other actor sent it a reference to actor B. So these key assumptions will allow us to do things like garbage collection. If we didn't have them, we would have no analytic power. So we're talking about actor garbage. In this particular example, which of these actors are garbage, right? Well, A, B, C, D, they're all currently busy and doing something, right? And at a high level, an actor is garbage if it can be removed from the system without affecting the system's behavior. And when I say affecting the system's behavior, it's a high-level thing. You can kind of imagine it if you had some kind of oracle that was monitoring all the files in the system and all the observable effects of the system. That oracle wouldn't be able to tell if the system was running with garbage collection or without garbage collection. The observable effects would be exactly the same. That's kind of what I mean in terms of this affecting the system behavior. But so from that high-level definition, what is garbage, right? Well, A, B, C, and D, they're all busy actors, but we're going to assume that our garbage collector isn't able to inspect the actor's code. It's not able to tell what these actors are doing. And if you can't tell what the actors are going to do, then potentially A, B, C, D, they could all potentially be writing to files or writing to databases. We have to be conservative, and we just have to say, if an actor is busy, pessimistically assume that actor is not garbage. It might have an effect on the world. So busy actors are not garbage. But let's say the system evolves to this state over here where you have some idle actors. Now, which of these actors are garbage? Well, even though none of them are busy right now, this actor D over here is about to receive a message. Oh, sorry, I just realized that Tianyin, you had your hand up. Go ahead.
No, like it was an early question. So just to clarify that, actor is single-threaded, right? Every actor is single-threaded.
Mm-hmm. That's right.
So that's like an assumption, basically, like
yeah.
Codes.
That should be, I should have been in my list of assumptions, okay. Is that, yeah. And so that's the thing, is it's either currently processing a message, and then it's a sequential entity that's either processing a message right now, or now it's just sitting there waiting for a message. It can't do two things at the same time. It can't process two messages at the same time. Yeah. So back to this example, we were trying to identify which of these actors are garbage. And even though actor D isn't busy right now, it's about to become busy when it receives this message. So D isn't garbage because it can affect the world potentially once it gets the message. Similarly, actor C, it's not going to receive a message right now, but D will be a busy actor with a reference to C. So because we're not looking at actor code, D might send a message to actor C, and C might be busy. So both D and C right now, we have to pessimistically assume they're not garbage. That leaves actors A and B, which you'll notice that they're just idle, they're sitting there, and no actor can actually ever send them a message. And what that means is that these actors are actually stuck in the idle state. They're never going to do anything. And what that means is they'll never have any effects. So these actors that are stuck in the idle state are what we're interested in this talk. They're called quiescent garbage because they're just sitting there doing nothing. And in this particular example, actors A and B are the quiescent actors. We're going to be working on detecting quiescent garbage. There's actually more forms of actor garbage in the literature. We can talk about that at the end of the talk, maybe in the Q&A, how this approach works in those settings. But for now, we're focusing on these idle actors, these stuck idle actors. And the most interesting part of this problem, though, is that faults can cause actors to become quiescent. So, for example, the kind of faults I'm going to be talking about in this talk are crashed nodes. And in Akka actually has a special mechanism for dealing with crashed nodes. So if a node appears to have crashed, then the other nodes in the cluster will forcibly remove it from the cluster. They'll exile it from the cluster. And so that holds regardless of whether the node is actually crashed or whether it's just behaving as if it's crashed. Maybe they're due to a network partition or something. And so if this node has been exiled, what happens then is, notice that now actor D can never receive this message because it's been removed from the cluster. And even if it did receive the message, it would never be able to have any effects that are visible on the rest of the cluster over here. It'll never be, if it sends a message, that message will never be delivered to C or A or B for that matter. So what this means is because node 3 has been exiled, actor C has become garbage. If it hadn't been exiled, D would be able to send it a message, but because it's been exiled, D can't send it a message anymore. I hope that's clear, because this is kind of a key part in this talk that we're focusing on. So, and this is the kind of garbage that no previous actor GC is able to deal with. And it's the one that we're focusing on in this talk. So now on to this topic of detecting garbage. Now that we know what it is, why don't we just stop the world and find all the garbage actors, right? Meaning you pause all the nodes, the garbage collector goes through every single node and figures out, here are all these actors, here's what they're doing, here are the garbage ones. Perfect. The problem is that that's, of course, has a huge performance impact. And also, it's kind of unclear what that would mean when you're dealing with things like exile. So we need some kind of more sophisticated approach than this. And this is where I get into the prior approaches to actor GC. They're trying to collect garbage without stopping the world. Now, one of the simplest form of actor GC, and it's actually used, I believe, in the Ray actor framework. Well, Ray is a framework that has actors. I'm not sure if they call it an actor framework. Is reference counting. And so the idea of reference counting, just like in a language like Python, every single actor has a count of how many other actors have references to it. And actors need to send, when actor A, for example, says, I don't need a reference to you anymore, it'll send a message, a decrement message, saying, you can decrement your reference count. The reference count is decremented to 0. And now B says, nobody knows me, nobody can send messages to me, I can garbage collect myself. Hooray, it's a very simple process. The main disadvantage of these approaches, though, is that they can only collect acyclic garbage. So if you look at these actors C and D that have references to each other, they both have to pessimistically assume, well, I might not be garbage because this guy might send me a message. But they're actually both idle, and they're both going to be stuck in this idle state forever. And so this cyclic garbage is not collected by reference counting, and it's arguably more of a problem with actor systems than in something like Python or Java, because actors are these processes that often talk to one another. So these bidirectional links that I showed here are I believe, quite common in actor systems that we need to deal with. So what's another approach? Another approach is what I call a snapshot-based approach. And in this approach, these actors take snapshots of their local state, and they send that to the garbage collector. The garbage collector combines all those local snapshots to form a global snapshot. And that global snapshot is hopefully a property that we call consistent. So this is just like the Chandy-Lamport snapshots for those of you who've taken your distributed systems classes. And it's just as if we had stopped the world and collected all the information. But the novelty of these snapshot-based approaches is that you don't need to stop the world. You just need to do a little bit of extra coordination in order to make sure that your global snapshot is consistent. And to illustrate the need for this consistency, you have this little diagram on the right. You have these actors A and B that are passing messages back and forth, right? Passing messages back and forth, and they're never going to become garbage because they're always going to eventually become busy. Now, if the actors take their local snapshots without trying to do any kind of consistency, we get a problem. So suppose right now, actor B takes a local snapshot and it says, well, I'm idle right now. I have a reference to this guy, and there are no messages in my mailbox. Now, actor A sends a message, and it takes a snapshot. And it says the same thing. I'm idle. I have a reference to this guy. There's no messages in my mailbox. And if you take these two snapshots, you put them together, they look like they form this consistent global snapshot, but it shows a thing that never happened in the real world, which was that A and B were both idle and they had references to one another. So if the garbage collector, if we don't have consistency, if the actors aren't careful about when they take their local snapshots, the garbage collector might falsely assume that these actors are garbage when they actually are never garbage. So the main disadvantage of this approach, though, is that this consistency requires extra synchronization, like locks and memory barriers and things like that. And another disadvantage is, anecdotally, is that it seems to make it difficult to deal with faults, like crash nodes and things. So these are kind of two issues with snapshot-based approaches. We want to move past those. Now, the approach that I'm going to focus on in this talk is what I call a collage-based approach.
Yeah, before you move on the snapshot, typical, like in distributed systems, when you take a global snapshot, there is a notion of being causally consistent, right? So there's these consistent snapshots. Wouldn't that address your issue? Because I think the main issue here is the fact that you're not taking a consistent snapshot, you're taking them inconsistent.
Yeah. That's exactly what I'm saying, is that these snapshot-based approaches, they need to do coordination in order to be causally consistent. So that causal consistency is what I mean by consistency here. So, you know, in the Chandy-Lamport snapshot, they're sending these messages, these marker messages, right, in order to make sure that the timing is correct. Right. And when you try to adapt that, so in the Chandy-Lamport snapshot, that's a fixed topology with very strict assumptions about message order and so on. And when you're adapting that to actors, and this prior work basically adapts the Chandy-Lamport snapshot algorithms to actors, and they end up having to use lots more messages. They have to use extra synchronization because it's this dynamic model. It becomes more complex, and that adds the synchronization cost. Yeah.
So the issue with Chandy-Lamport adapted to actors is one of overhead. Is that what you're saying?
One problem is overhead, and the other problem is that it seems to make it difficult to deal with faults. Like the Chandy-Lamport snapshot, what happens if a node crashes? You can't really obtain a global snapshot. You'd have to adapt it somehow. And prior work has kind of used hand-wavy things of about how we can adapt it when a node crashes, but it's kind of unclear what you're supposed to do when a node crashes.
And so your collage-based approach will address both the overhead and the faults aspects.
Mm-hmm. Yes. But it's not my collage-based approach, because there is one prior work that I'll talk about that uses, but I come up with the term collage-based approach. And the idea here is that actors take their local snapshots without any kind of coordination at all. And they send them to the garbage collector, and the garbage collector collects some local snapshots. They might not even be global. It might not have local snapshots from every actor. So it gets these local snapshots without coordination, and they form this thing that I call a collage, right? It's kind of a pun playing on snapshot there. And the idea is that the garbage collector retroactively figures out which subsets of that collage are consistent with one another, and it uses that in order to collect garbage. So I have an example here. Probably the most successful actor garbage collection, or currently the most renowned actor garbage collection algorithm, is in the Pony actor framework. And the way that it works is these actors send their local snapshots to the garbage collector. The garbage collector gets some snapshots, and it figures out, here are these actors that look like they're quiescent. Remember, we don't have any coordination. We don't have any consistency, so they might not actually be quiescent. And in order to figure out whether they're quiescent or not, it performs this confirmation protocol. It sends a confirmation message to the actors. They send back an acknowledgement or a not acknowledgement. And I don't have time to explain why this works, but it performs this confirmation protocol, and that allows it to figure out retroactively which of those snapshots were consistent. Now, the main disadvantage of this approach, though, is that that confirmation protocol that they use requires causal message delivery. And Akka and Erlang, they don't provide causal message delivery in the cluster, and that would introduce some overhead in order to do that. There's also, well, I'll leave it at that. So there's that, and also this actor GC approach, just like all the other ones, doesn't deal with faults. So that's another thing that we want to, doesn't recover from faults. So those are the two things that we want to approach. And now I introduced my thesis, which basically takes this approach that was used in Pony, and I remove the need for the quiescence confirmation protocol. Basically, with a very simple thing, we just add extra information to each actor's state. And what this will mean is that once the garbage collector gets a collage, all the actors that appear quiescent will actually be quiescent without any form of confirmation. It's kind of a little bit of a magic trick here, and I'll explain how that works in this talk. And so in part one of my thesis, I use this collage-based approach, and I combine it with reference listing, which is very similar to what Pony does. So reference listing does the acyclic, and the collage-based deals with the cyclic garbage. And in part two, which I focus on in this talk, is camera's blocking the view. The first, I use the collage-based approach in order to develop a first fault recovering cyclic actor GC. So let's get into the theory, I guess. So in order to say what it means to appear quiescent, we need to say what it really means to be quiescent. Because I've characterized quiescence before as being stuck in the idle state. But if you have a collage, what does it mean to actually look like you're stuck in the idle state? When does this happen? And I have to introduce some terminology in order to do that. Number one, we'll have this term unblocked. And unblocked is basically a generalization of the notion of busy actors. So here, actor X, an actor is unblocked if it's either busy right now or it has an undelivered message. So it'll be busy kind of in the next step. And this diagram, which of the actors are unblocked? Well, you've got A and E are busy, and F and I are actors with undelivered messages. So these highlighted actors are the ones that are currently unblocked. Simple enough. We also need this notion of potential acquaintances. So actor A is potentially acquainted with actor, or actor X is potentially acquainted with actor Y if X has a reference to actor Y, or there's an undelivered message to X that contains a reference to Y. So this is a generalization of the notion of references. So following this definition, which of the actors are potentially acquainted with G? Give a moment to think. F and C, they both have references to G, so they're potentially acquainted. And actor I, even though it doesn't have a reference right now, it does have this undelivered message that contains a reference to G. So that means that it's also potentially acquainted with G. Now, the reason I introduced this terminology is it's crucial for quiescence. Notice, for example, that the unblocked actors are not quiescent, right? Because quiescent actors are stuck in the idle state, and these actors are all either currently busy or they're about to become busy. It's maybe obvious. But also notice that if an unblocked actor's potential acquaintances are also not quiescent, if we're not analyzing actor's code. For example, this actor I over here, once it receives this message, it'll be busy and it will have a reference to actor G. So it's an unblocked actor that's potentially acquainted with actor G. And once it's busy, it will be able to send a message to actor G. G can become busy. Now it's not quiescent. So potential acquaintances of unblocked actors are also not quiescent. And we can use this in order to come up with a tight characterization of what it means to be quiescent at a given moment in time. It means that an actor is currently blocked and that every actor X that is potentially acquainted with it is also quiescent. So for example, this actor B is blocked and there are no actors that are potentially acquainted with it, so it's stuck in the idle state. Meanwhile, these actors C, D, and H, they're all blocked, they're all potentially acquainted with one another, and they're all quiescent, basically, because they're all just stuck in this sort of deadlock shape. Now, maybe this is a hard definition to wrap your mind around, but the key idea is that we define quiescence in terms of blocked actors and the potentially acquainted, potentially acquainted actors. So we've kind of reduced our problem from finding quiescent actors to finding which ones are blocked and which ones are potentially acquainted. So our approach is going to be, first, I know that consistency is the goal, that causal consistency is the goal, but we're going to suppose that the collage is causally consistent. And a recap, so what that means is the collage corresponds to something that happened at a given moment in time. It's as if we stopped the world and collected this collage. So we're going to first assume that it is consistent, even though we're not going to assume it later on. And assuming that consistency, what kind of information would we need each actor's state to contain in order to tell if it's blocked or unblocked? And what kind of information do we need to store in each actor's state in order to tell who is potentially acquainted with whom? And once we add that information to each actor's states, we're going to magically get consistency out of this. So that's the cool magic trick that I'm going to pull by the end of the talk. So starting with the unblocked actors, and let me pause for a second to have a bit of water in case there's any questions about this project. Okay, so let's use this approach to figure out which actors are unblocked. So here I have this kind of a depiction of a collage. We have snapshots from A, B, C, F, and H. A's snapshot says that it's idle and I don't have any references to any actors. C's snapshot says I'm idle and I have references to actors H and G. B's snapshot says I'm busy and I don't have any references. And I'll be depicting collages instead of this way as this kind of graphical representation. So I hope you can see the connection between this and this representation. We just visualize those references in the graph. And the question marks correspond to references. For example, we had this actor C has a reference to G, but G doesn't have a snapshot. So that's just marked as a question mark here. So now that we have this collage and we're looking at it, what information do we need from this collage in order to figure out which of these actors are unblocked? Because remember, a collage just contains an actor's state at a moment in time. It doesn't contain any information about messages. We need to figure out, we need to add information in order to figure out information about messages. So in particular, let's look at this actor A. How would we tell if this actor A has undelivered messages? Well, I think the most straightforward approach is to keep track of message counts. So each actor is going to keep track of x.received, the total number of messages that it's ever received. And for each other actor, Y, it's going to keep track of how many messages it's ever sent to Y. So I've added that here to the diagram. A has received 5 messages. F has sent A 1 message. C has sent A 1 message. Over here, H has sent A 3 messages. And the idea would be just to compare the total number of messages that have been sent against the total number of messages that have been received. And by the way, because this actor B has nothing, it implicitly means I've sent A 0 messages. So the idea is that A is blocked if the total send count, you add up all the send counts, equals the receive counts. In this case, 1 plus 3 plus 1 equals 5. So we would say it looks like A is blocked. Now, this is contingent on a key assumption, though, which is that every actor that has ever sent messages to A is in the collage, right? Because if we had this extra actor D that suddenly pops into the collage and say, hey, by the way, I've sent A 2 messages. It used to look like A was blocked, but now 1 plus 3 plus 1 plus 2, I don't know what that adds up to, but it's greater than 5. So now we would conclude that A is unblocked. So basically what I'm trying to say is we use these message counts, and we also need to make sure that the collage contains snapshots from enough actors in order to tell if something is blocked. So how do we do that, though? How do we make sure that the collage contains enough information? Because one of the key things that we're trying to do is we're not going to require the collage to be global. We just want to have, given, 5, 10 snapshots, what can I do? What can I conclude from those 10 snapshots? And the approach I propose is a very lightweight approach. Oh, I should mention, by the way, that actors, they don't know who has references to them in general, because these references are just floating around as addresses. And if you wanted to add that into an actor system, you'd have to use something like reference listing. Each actor keeps track of who has references to it. And that adds overhead, basically, that we don't want to introduce. So instead, I have this lightweight approach, which I call contact tracing. Credit to the COVID-19 pandemic for giving me the name. Thank you very much, COVID. And here's how it works. I think it's very straightforward. The idea is that when this actor B spawns an actor A, that child is going to be born with a pointer to its parent. And I visualize that with this kind of trace here. There's a pointer from A to B. And the idea now, I hope you can see where I'm going with this, is that whenever B sends another actor a reference to A, it's also going to add contact tracing information. So it leaves a trail of breadcrumbs from A to all of the actors that have ever received messages to A. So on. So these actors receive these message references, and this trail of breadcrumbs, this contact trace has to be retained even when the actor B forgets its references. So now it's dropped these references, and now there's a path from A to B to D, A to B to G. And this contact trace continues as these other actors do this. And if you remove all the edges, you can see that there's always going to be a path from A to every actor that's ever been potentially acquainted with A. That's how contact tracing works. And this, I hope you can see, is now coupled with the message counts, will let us get to where we want to go. So we can use this notion of what it means to appear like it's blocked with the contact tracing in order to define what it means to appear quiescent. So an actor appears quiescent if, number one, it appears idle. And on the right, I'm going to highlight all the actors that are disqualified by this definition in this particular collage. So an actor that appears quiescent has to appear idle, which means that it was idle in its latest snapshot. And all the actors that sent messages to Y have to be in the collage. So in this case, actor C is disqualified because there's a path from C to D to this one. So we can't tell whether C appears blocked or not. The actor has to also appear blocked. So over here, this actor 2 plus 2 plus 2 is greater than 3. So this actor is disqualified from the definition. And also, if X appears to be potentially acquainted with Y, then X appears quiescent. So this means basically because because J has a reference to H, it means that H is also not quiescent. And basically, you go through this process of disqualifying actors until you're left with the apparently quiescent actors, which satisfy all these properties. And in this particular collage, it's just these two actors that appear quiescent. And I want to give you an impression. The proof is actually quite involved, but I want to give you an impression for how we get this consistency property out of this. How do we get that actors that appear quiescent are quiescent? And this is just kind of an impression, a flavor. You can get the full thing in the thesis. So the key idea of the proof is that you have this set of actors Q. They're the ones that appear to be quiescent, right? And let's say that actor B is, for a contradiction, the first actor that appears quiescent to take a snapshot and then receives a message. And this is a contradiction because all the actors that appear quiescent, they're supposed to never receive any messages, right? So let's say that B receives a message and it's the first one to receive a message after taking a snapshot. Well, where did this message come from? It must have been sent by some actor. And thanks to contact tracing, we know that every actor that has ever sent a message to B, will also have to take a snapshot. It will also be in the collage. That's what contact tracing is going to guarantee for us. And so because of that, we're basically reduced to two cases of who could have sent the message. Case one is that actor A, some actors took a snapshot and then sent a message. And case B is that some actor sent a message and then took a snapshot. Let's look at case one first. Notice, though, that when this message was sent, what the definition of apparent quiescence guarantees is that this actor also has to appear quiescent. If this actor appears quiescent, this actor has to appear quiescent as well. And this immediately contradicts our assumption that B was the first actor to receive a message after taking a snapshot. Because in order to send this message, this actor must have taken a snapshot and become busy before this one. So it's an immediate contradiction, just because we assumed that this was the first actor. The meat of the proof is this part, where some actor sends a message and then takes a snapshot, and B takes a snapshot and then receives a message. This is where the message counts come in. Because if you'll notice, B has a receive count of 1. It's received one message. But in this diagram, it doesn't look like any actor has ever sent it a message before this. So how did this receive count equal to 1? The only way that it turns out that this can happen is if some other actor A sent a message after taking a snapshot and it was received before B took a snapshot. So in Chandy-Lamport terminology, this is a backward crossing message. The only way for there to be a forward crossing message is if there's a backward crossing message. And now we're back where we started, because this actor A must have received a message in order to become busy, and it must have received that message. Sorry, that was so distracting. It must have received that message before B became busy. So that's the other part of the contradiction. These message counts do this. Okay, so that's the basic idea. And I want to get into how we do the fault recovery. So we had this idea, remember, that a node is exiled if it appears to have crashed, and the other nodes have kicked it out of the system, right? And so exiled nodes, if you take this existing collage-based approach that we've developed, they can prevent garbage from being collected. So here's an example where you have this actor A, it's sent 5 messages to actor B. B knows that A has a reference to it, and A also has a reference to this actor C. And what happens, let's say that A sends a couple of messages to B, and it sends C a reference to B. And when it does that, it extends the contact tracing information like we wanted it to. Now, if A's node crashes before A takes a snapshot, then we're in a problem for B, because we'll never know how many messages A sent to B. So we'll never be able to tell if B is unblocked. And we'll also never know how many references A created. We don't have access to the contact tracing information as well. So this is why exiled nodes are such a problem for garbage collectors. They contain this information that the garbage collector needed in order to collect this garbage, and maybe this garbage as well. So the challenge that we need to overcome if we're dealing with crashes or exiled nodes is, number one, how many messages did A send to B before it became exiled? And number two, how many references pointing to B did A create before it became exiled? Now, the trick that we're going to use is we're not going to answer these questions. Instead of saying, how many messages did it send, what we really care about is how many messages can actually make it to this node, and how many references can actually make it to this node. And that's a very different question than how many messages did it send. So the approach I use is to associate every single node with what I call an ingress actor. And this ingress actor is responsible for pre-processing every single message that gets delivered to the node. And this is actually what Akka, the Akka actor framework does. It has these process that deserializes messages and so on. So we can just hook into that, right? And the idea is, instead of sending messages, A sending messages directly to B, it sends a message to the ingress actor, which forwards the message to the actor B. And this ingress actor keeps track of information as it streams into the node. So right now it says that I've received 5 messages that are directed towards B. And when this message M1 gets sent to the ingress actor, it increments that count. Now I've seen 6 messages come in to B. And similarly, this ingress actor up here, it'll keep track of references. So it will say, aha, I've seen a reference owned by C and pointing to B. And the point is that now when A's node becomes exiled or it crashes, we don't need the information from that node at all, because the information is actually stored at these ingress actors. And so the fault recovery procedure in the theory is, instead of getting snapshots, we replace the snapshots from this exiled node with snapshots from all of the ingress actors from all the healthy nodes. And that's the basic approach. So in summary, with this theory that we've developed, actors can take snapshots with 0 coordination, no locks, no causal message delivery. They just take these snapshots whenever they like. And in order to recover from exile, you just need snapshots from all of the healthy ingress actors. So we can actually do this with the collage-based approach. It's interesting to think about whether you could do this with other approaches, but we've done it here with the collage-based approach. And in the thesis, I cover a lot more extensions that I don't have time to talk about here. Recovering from dropped messages, actors throwing exceptions, setting timeouts and crashing, actors monitoring one another for failure. This is one of the most interesting components because it changes what it means to be quiescent. And I give full proofs of correctness and formal specifications for this. So not the end of the talk yet. This has just been theory land. I want to talk about the implementation and the evaluation in Akka.
A couple of questions. Can you say, like based on the previous discussion, the big difference between this one and the previous work is that you're efficient and you're fault tolerant. So I'd like to hear a little bit about how you're fault tolerant. I have a second question on the efficient front, which is that sounds like you're counting the number of messages, but your messages contain a lot of information. So are you also counting the bytes or the actual bandwidth that's being used in the...
Yeah, let me address make sure I remember all the points of the question. I'll start with the end. We don't need to know what is the payload of the message. We only need to know how many messages there were and how many references those messages contained. And also, by the way, those actor snapshots, they don't contain all the information that the actor has if it has some large data structure. We only need to know what are the references, is it idle or busy, how many messages have you sent, and the contact tracing information. That's all the information that we need there.
So that's fine. That I understand. My question was really more about a metric. So your metric for overhead is number of messages and not number of bytes. Is that correct?
So in terms of overhead, we should talk about compared to the Pony algorithm required causal message delivery. So there's a lot of different metrics along which the overhead changes, right? So in this case, we allow unordered messages, and Pony requires causal message delivery. So that's some overhead that we avoid there. And we also avoid the overhead of the confirmation protocol, because the garbage collector in Pony had to check whether these actors are actually quiescent. And we already know that these actors are quiescent. But you're right that the trade-off, instead of sending those messages instead of having causal message delivery, is we have additional memory. And in fact, in this theoretical model, which I'll address in the implementation, we have O(n) squared memory. So that's a thing that needs to be addressed in the implementation. Because remember, because every single...
Right, I think that's important, yeah.
Because every single actor, if you have n actors and every actor sends messages to every single actor, then each one of them has n send counts, and n times n is n squared. And that's the thing that we address in the implementation, actually. But yeah, the trade-off is memory.
Okay. And then the other question was fault tolerance. If you can give a high-level overview of how you address failures, that would be useful.
Yeah, so what we do is, number one, the garbage collector has to find out that this node has been exiled. And once it finds out that the node has been exiled, it needs to get recent enough snapshots from these ingress actors. And these ingress actors, by the way, they're at the meta level. They're part of the garbage collector. They never crash. So once it figures out that this is exiled and it has snapshots from these ingress actors, it replaces all of the snapshots from this node with the snapshots from the ingress actors in the collage. And that will make it so that if an actor, so for example, if this actor A held on to this actor B before, it had a reference to this actor B. So in the old collage, we couldn't garbage collect B. But now that this thing has been marked as exiled and we have these new ingress actor snapshots, B says, this guy no longer has a reference to me anymore. And in fact, once this message is delivered, presumably this actor B will be able to be garbage collected in this new version of the snapshot, in the new version of the collage. Does that cover it?
And how do you deal with simultaneous failures, like if that second node also fails while you're doing the recovery?
Yeah, that's perfectly part of it, actually. So to get more into detail with those, the way that we actually detect that this node is exiled is every single ingress actor, it keeps track of whether... So when this node has failed, the exile is actually not an atomic process. What happens is, first, this node does something called shunning this node. It says, I'm no longer going to accept any messages from this node anymore. And that will set up forward a chain reaction where eventually this node will also say, I'm going to stop receiving messages from this node. And once all of the ingress actors have all voted to say, like, we're not receiving any messages from this node anymore, now this thing has actually been exiled. And these ingress actor snapshots contain the information about whether the thing, what nodes have been exiled by what ingress actors. And so what the garbage collector sees is it gets these ingress actor snapshots. And once it sees, oh, all of these ingress actors at nodes 1, 2, 3 have all shunned nodes 4, 5, 6. We're able to conclude we have recent enough ingress actor snapshots, and we've also concluded that these nodes have all been removed. So I do address this in the thesis kind of in more detail, but it becomes hairier and harder to deal with.
Okay. No, I guess my concern is what happens if the ingress actors also fail, so that there is, no way for the system to know, who has failed, because you can have multiple failures, right? That's it sounds like you're relying on the ingress actors to do the failure detection in agreement, which is fine as an approach. But then the ingress actors may themselves fail, in which case you need their ingress actors to be able to detect their failure, and those might fail, and so on and so forth. And you're going to have multiple simultaneous failures. So just wondering if you address those aspects.
I definitely do. Specifying it's not the ingress actors that fail, it's the nodes that fail, right? We're assuming that as long as this node is up, the ingress actor is up.
What I mean, yeah.
And so what I didn't show in this diagram is that there's also an ingress actor. There's ingress actors between every pair of nodes. So let's say let's consider that scenario, right? So we have a snapshot from this ingress actor, and it says, hey, I noticed that I've shunned this guy. And now the garbage collector, it receives a snapshot, and it's basically either going to wait to get an ingress actor snapshot from this, or if it never arrives because this node has crashed, then we're going to get an ingress actor snapshot from this ingress actor. Basically, this node will have kicked this node out, and we get a snapshot from this ingress actor. So the multiple failures are addressed.
Okay. The other question I had about failures was some of these failures might be false positives. So it may be a node that is just happens to be slow, but then comes back online after a little while, after you've detected that, oh, it's failed. How do you deal with that? Do you force that node to leave and then rejoin, or do you kind of integrate it back in?
Yeah, this is exactly what Akka does already. Is if the node has been, that's what I mean by exile, is that the node, regardless of whether it was actually failed or not, it's been forced out of the cluster. And if it wants to rejoin, it needs to kill all the actors that are here, and it needs to rejoin as a fresh node. And we're hooking into that mechanism. And if we didn't have that, there's basically no way that we could do this fault recovering mechanism, because if this node could rejoin and this actor could start sending messages again, well, the whole point of this fault recovering thing was we concluded this actor is definitely not going to be a problem anymore. If you're, if that makes sense.
I guess there is an associated question, but I can hold off on that until the implementation, which is obviously you're going to have a lot of timeouts here. Anytime there's failure detection, there's timeouts, right? So the high level question I have is how aggressively do you set the timeouts, and what rules of thumb do you use to set the timeouts? But you can address that in the implementation.
You're talking about the when does the node get exiled?
Yeah.
That's built into the Akka actor framework, actually. I just use whatever Akka uses, and Akka has configurable timeouts.
I see. Got it. Okay. All right. Thanks.
Yeah, specifically they use fee detection, fee accrual.
Oh,
is what they use. Yeah.
The suspicion based.
What was that?
I have a question. Just because it connects to what Indy was asking about. So when you exile a node, and or more generally, from what I understand, your approach currently does not allow new nodes to join dynamically.
Yeah, that's one of the assumptions that I make, is that new nodes don't join dynamically. I think that it can be extended to that, but that's it's not something I've covered right now. Okay, you can kind of maybe model it. I think you can probably model it as if all of the nodes are ever going to join have joined at the start, but they only come online. They only start doing things at a certain point in time t. I think that's how I would model it in practice. But,
okay, yeah. I just wanted to clarify.
That's a great question. And I should mention, though, that I'm not the one that's doing the exile. This exile is a mechanism that Akka has and that we hook into it. And this is actually a problem that Erlang doesn't do this. And because Erlang doesn't do this, it doesn't have this exile mechanism. you can't implement a fault recovering garbage collector. You can only make one that is fault tolerant, which means that if a node crashes, things can still be garbage collected, but we have to pessimistically assume that that node can always come back up and start sending messages again. And I addressed this in my thesis as well. Yeah. Any further questions before we move on? Okay, let's get into the implementation. So here are some various notes on this theory that I've developed so far that we want to address in an implementation. Number one is that, I don't know if you've noticed, but the actor states are growing monotonically. Every time I send a message to an actor, I need to keep track of that in a count. And if I start sending messages to all these different actors, I need to keep track of every single little send count on every single actor. And theoretically, the memory overhead of that is O of n squared. And we also had this kind of notion of an omniscient God of a centralized garbage collector. We probably don't want to have a centralized garbage collector in practice. For one thing, how does the fault tolerance work in that case? And third, I didn't even address what is the algorithm for actually finding the quiescent actors? How fast can we do it? What's the complexity of finding quiescent actors in a collage? So that's what we want to address in the implementation. And so I've implemented this theory, this collage-based approach, in something I call CRGC, which is an actor garbage collection for Akka. It's based on or inspired by conflict replicated data types, CRDTs. You don't need to know what CRDTs are in detail in order to understand the talk, but if you do see those, you'll see a lot of similarities between the garbage collection approach and the CRDT approach. And so here's how it works, step by step. Every single node is going to have its local garbage collector. And actors, instead of sending snapshots, they're going to send incremental updates that I call diary entries to their local garbage collector. So if, in the past 5 seconds, I've sent 3 messages, I've created 2 references and so on, that piece of information will be in my diary entry, and I send that to the garbage collector. And those incremental updates, we can configure how often those updates are sent and how big those updates are. And the local garbage collectors, they exchange batches of the diary entries that they've received so far in the form of these delta graphs. So we could just as well have had every single actor send diary entries to every single garbage collector, but the memory representation of those diary entries would not be very efficient. So these delta graphs are just a compact form of batches of entries. So they exchange these delta graphs. And once garbage collectors get these delta graphs and these entries, they use those continually to incrementally build something called a shadow graph. And a shadow graph is just an efficient representation for a collage that will make it very fast to figure out which actors appear to be quiescent. So it incrementally builds these shadow graphs with the entries and delta graphs it's received so far. And they periodically trace their shadow graph at a configurable frequency to figure out which of the actors on my node are quiescent. And you'll notice that these 2 garbage collectors, they have different shadow graphs. They have different views of the system. And that's because they've received different batches of entries and delta graphs. But we have this property that they are eventually consistent. So if these actors eventually stop doing stuff, they stop sending entries, and the delta graphs eventually get propagated, eventually these garbage collectors will converge to having the same shadow graph. They'll have the same view of the system based on all those entries. And for fault recovery, the local GCs incrementally build these undo logs for every single remote n. And what happens is when this node over here is exiled, this garbage collector detects that, it will use its undo log for the left node and apply it to its shadow graph in order to get a new shadow graph that concludes, aha, this actor is now garbage, and it will collect that garbage accordingly. So that's the high-level architecture. I'll go into a little bit more detail. But I think, how are we doing for time? I don't have a clock with me, 10 o'clock. Well, I'll go through it. I think we might have time. So for example, we've got these diary entries, and they replace these snapshots. Because remember, again, these actor states, they're cumulative. They're building up more and more information. And instead of sending these snapshots, which overlap with one another, we break them down into individual diary entries that have fixed size. This leads to a lot of interesting optimizations that I think I'll skip for now, but we should maybe talk about them in the Q&A. Object pooling, multiple message queues, frequency of entries being sent out. And you've got these delta graphs, which are batches of diary entries. But we'll skip over that for now. Let's talk about shadow graphs. So in the CRGC, which is the implementation, collages, instead of being represented as just a bunch of snapshots, they're represented as graphs called shadow graphs. And in the graph, the nodes of the graph over here correspond to actors, and the edges correspond to references. And so this is how we reduce that memory overhead from O of n squared to O of n. Because instead of, in the original collage representation, every snapshot had all these separate send counts, and all these receive counts. And in the shadow graph, instead of representing all the send counts and all the receive counts separately, we just combine them into one value, because all we cared about was whether an actor was unblocked or not. So we just add up all the send counts, we subtract it from the latest receive count, and that gives us our value. So instead of, particularly if we have this actor C, instead of storing send count for this, send count for this, and a receive count, we just say C.undelivered, which is there's one message that appears to be undelivered to me. I hope that makes sense. So instead of storing n send counts, we just store 1. And if an actor is unblocked or appears to be unblocked in the collage, it's going to be marked as a pseudo root in the shadow graph. And what that means is everything that is reachable from a pseudo root is going to be not garbage. So the C is a pseudo root, it's not garbage, and you can follow these references to conclude that this is not garbage. Whereas this, on the other hand, there's no path from a pseudo root to this actor, so this one is garbage. So the GC, all it does is it just does this tracing, and if you know anything about garbage collection, you know that that's just how a regular garbage collector works. It just traces a path from the root set to all of the actors that are, to figure out which of the actors are not garbage, and it collects all the actors that are not marked. So that's what we do in this with the shadow graph. So the takeaway is that tracing is fast. It's as fast as it is in a sequential implementation. And I want to talk about undo logs as well. So talking about recovery from faults, if in order to recover from an exiled node N1, every other node N2 would need to do the following things. This is the naive approach. First, it needs to undo all of the changes that that node made to its shadow graph. And then it needs to apply all of the snapshots from each of these ingress actors to its delta graph in order to compute a new delta graph, right? So you've got a shadow graph, remove the changes that this node made, use the ingress actors to compensate for it. Now, the reason I call this a naive approach is that this extra information is monotonically growing. This is like the fault recovering information. It's just growing and growing and growing, and that basically is a memory leak. We can't have that. The way that we address this is by observing that the delta graphs that the garbage collectors receive from the other nodes contain complementary information to what the ingress actors snapshots are saying. So a delta graph will say, hey, I'm a garbage collector. I have this actor A. It sent 3 messages to your actor B. And what an ingress entry will say is, hey, I'm an ingress actor at that node, and I've received 2 messages so far from that actor A going to actor B. And so instead of storing those 2 integers separately, we're going to combine them again. We're just going to subtract them in the form of this undo log. So the undo log for each node says, here's a recipe. In case of failure break glass, right? If node N1 is exiled, decrement this actor's B.undelivered count. This is the recipe. And the nice thing about these undo logs now is that they converge towards emptiness. So if your actors eventually stop doing stuff, then the undo logs are eventually going to become empty. They're going to contain no memory. So we've dealt with this kind of memory leak that was happening in the previous example, and we get to keep our nice shadow graph representation here, which is fast for tracing. Yeah, that's basically it. So to recap, actors are sending their diary entries to the local garbage collector. Local garbage collectors broadcast the delta graphs, which are just batches of entries. And each local garbage collector incrementally builds a shadow graph, and it also incrementally builds undo logs for each other node. and then it periodically scans the shadow graph in order to figure out which actors on its node are garbage. And in case a node N is exiled, every healthy garbage collector, once it finds out that that node has been exiled, it's going to use its undo log in order to repair its shadow graph. So that's it for the implementation. I have an evaluation section and a conclusion, but I'll pause here in case there are any questions.
So then, like, I have a question about the ingress actor actually.
Yeah.
So where the ingress actor like sit in the current implementation?
Where does it sit?
Yeah. So like, is it in the local GC, or like it's actually for like every actor there is ingress actor there?
In Akka, every single node has a pipeline for deserializing messages that come from all the other nodes.
Mm-hmm.
And so I've hooked into that deserialization pipeline, and I intercept those messages and I count. I just check, who is this message destined towards, and does it contain any references? So I've just hooked into that pipeline. And so each node has, really what it has is just one ingress actor, even though in the theory we have multiple ingress actors. And this ingress actor keeps track of all the messages that have come in. Yeah.
Dan, I also have a question.
Yeah.
So for your implementation, you came up with a bunch of new interesting ideas, right?
Yeah.
And I'm just wondering if, because it's sort of it's a bit different from how you formalized things before. So what I'm wondering is, are these differences, like, should one consider them to be mainly, let's say, optimizations, because you want to avoid, things like a centralized GC. Well, that's maybe more than an optimization, but there are these mainly things, to make things actually practical, right? Or would there also be some value in sort of trying to have a formalization which is actually closer to your implementation?
Yeah, I absolutely do think that a formalization would be helpful here, because there's a lot of tricks ultimately they end up using that and questions that maybe we'd like to formalize. So I do agree that if it would be nice to extend the formalization to account for these for this new design. Yeah.
So I think rather than starting from scratch, obviously they built on that formalization, so the proofs should be essentially corollaries after the previous proofs.
Yeah, I think that's
because
what
once you have the previous proof, you'll take the difference, and then the proof should fall right out. So I don't think that should be too hard to do. You won't start from scratch. You're starting from the algorithm, and then.
Oh yeah, absolutely. Yeah, it's
the steps you should add, and the proofs should be fairly obvious.
Mm-hmm. Yeah, so what it would be is we'd probably prove some kind of equivalence between, we'd show that the shadow graph is equivalent to the collage representation. We'd show that these undo logs are equivalent to this. Exactly.
Right. Yeah.
They're not two completely unrelated algorithms. That would be pretty funny.
Yeah, exactly. Yeah. So, and you should do that for completeness in your plan, right?
Mm-hmm. Yeah, I agree. Okay, I'll get into the evaluation, and then we can conclude, maybe ask additional questions. So for the evaluation, I have a two-part evaluation. And this was kind of a tricky problem, because most actor systems don't have actor GC. So there's not a lot of existing benchmarks that can really leverage that. We're forced to deal with systems that were designed around the idea of manual memory management. So it's kind of unclear how to measure these things effectively. So what I did was I took these existing actor benchmarks, like probably the standard actor benchmarks is called the Savina suite. And this is a benchmark suite that collects various kinds of concurrency and parallelism benchmarks from shared memory and some actor stuff. And it's implemented them in Akka. And it uses manual memory management. And it's also on a single machine only. It's not a distributed benchmark suite. And so what I did was I ported the existing implementations of the Akka implementation to use my garbage collector. And the idea would be these things are already manually garbage collected. Presumably that's as fast as it can get. So we're just measuring with these Sabina benchmarks, how much overhead would it be if the programmer had written these benchmarks with automatic garbage collection instead of doing manual garbage collection. So the Sabina benchmarks kind of serve just as a guess of how what the overhead would be in a practical system. And I'll start with some micro benchmarks. Here we have this counting benchmark in which a producer sends messages as fast as it possibly can to a consumer. Here it sends 1 million messages, 2 million messages, 3 million messages, and this measures how much time it took. Notice that it's a log scale. But you'll see that, and so the blue line is always going to be with no garbage collection with manual memory management. And the other lines are two different versions of the garbage collection implementation. I'll talk about what those different versions are later if you're interested. But basically, we show that they behave very similarly. So this micro benchmark is basically measuring how fast can we put things into mailboxes. And this shows that those message counts that we did don't have very high overhead. They appear to have the very same scaling behavior here. So that's nice. And over here, we have this micro benchmark that is a stress test for spawning actors. You're computing the nth Fibonacci number by spawning an actor to compute the n-1th Fibonacci number and the n-2th Fibonacci number. It forms this big tree. And this is a real worst case scenario. I mean, it's a ridiculous thing to do because each actor, it does so little computation that the spawning and sending messages dominates the actual computation that these actors are doing. But it's just a stress test of how fast can we spawn actors, basically. And the blue line shows, yes, if you're doing manual memory management in this case, you're going to get better performance. But garbage collection scales pretty close within it along the same lines. So that's a positive. And there's also an interesting story about this orange line, which is with the original implementation of Sabina. And this is an optimized implementation that I wrote with manual memory management. This is the original Sabina benchmark, and this is this one. Because I was trying to understand why is my garbage collected benchmark performing better than a manual one, and it's because a subtle problem there that I can discuss later. Anyway, but this shows kind of, we do have some overhead here when it comes to spawning actors, but this is very much a worst case scenario. When you get to real benchmarks, like here we have guided search or quick sort, the difference, this overhead appears to completely vanish. We have the very same scaling behavior. It's within kind of margin of error here. And this quicksort benchmark, it's exactly the same concurrency structure as the Fibonacci benchmark, except the actors are actually doing work. And so the work ends up masking any kind of minimal overhead that the garbage collector has. And we see the same thing for all pairs shortest paths, n queens, matrix multiplication. There's a bit more variance in this radix sort. But overall, what these benchmarks seem to show is that if you're doing any kind of real work, a real application, presumably, the garbage collector adds negligible overhead, but adds this benefit of automatic memory management. So it seems to be a good sign, those benchmarks.
What is, Dan, what is the percentage overhead here? Because your y-axis is logarithmic, so it's very hard to make out.
Yeah, that's a good point. I should really compute the percentage overhead. I mean, they appear to vary. You know, sometimes the garbage collector actually performs better.
Fine. I think for each application, what I would recommend is you give a range, like the overhead is between X% and Y%. You just calculate the range. So I think that's right.
I'll write that down.
Yeah, especially in the Fibonacci. I mean, I think the Fibonacci is an extreme case, obviously, but Fibonacci, it seems to be at least an order of magnitude worse. So, in other cases, it's not that bad.
Yeah. Any other thoughts on these particular benchmarks? Okay, so the other component of the evaluation is I wanted to have a distributed benchmark, and I wanted to show a case where the actor garbage creation is unpredictable. Because in the previous benchmarks, they're designed around the idea that, well, you know when to garbage collect an actor. You wouldn't write an actor system where you don't know how to garbage collect the actors because you don't have an actor garbage collector. So I made this benchmark that is a configurable, tunable benchmark that you can configure the various probabilities in order to mimic various kinds of workloads. And it generates actors in a way that's entirely unpredictable, so that if you wanted to garbage collect these, you'd have to basically write your own garbage collector. And in this benchmark, each node has a manager actor, and it receives a stream of requests. And it can, when it receives a request, it can spawn some workers, send work to the workers. The workers can also spawn workers and send messages. And this architecture is inspired by a lot of the benchmarks that are in the Sabina benchmark suite, and also inspired by another benchmark that I haven't mentioned in the slide, which is the chat app benchmark that was designed similarly to this one to be tunable to adapt to various kinds of workloads. So this wasn't an out of the blue benchmark. It was adapted based on these existing work to try and, but adapted to a distributed system and also adapted to generate garbage, because that's what we're trying to study here. And we don't get very much surprising results here. We just find that if you're doing this benchmark with no garbage collection, eventually the worker actors start to clog up the system and the system crashes. Whereas if you have garbage collection enabled, you have the JVM garbage collector periodically kicks in and it collects all the memory here. So we get a nice steady curve and we get no crash. So basically this is just showing, indeed, garbage collector collects garbage actors. Hooray, that's really nice. So to wrap up, I've introduced the first fault recovering cyclic actor GC and proved it correct. I implemented their approach in Akka, and it seems to perform well in these benchmarks. But the most straightforward extension of this would be to deploy it in a real Akka system. And this will be a lot of technical work. Akka has a huge API. They have things like persistence, event sourcing. They have something called the receptionist actor. You have to convert all this API to that. So that will be an interesting project there, deploying it into an existing system and finding out how it performs there. It would also be interesting to extend this approach to more general forms of garbage. I've just talked about quiescent garbage throughout this talk, but there are more general kinds of garbage that have been addressed in previous work. So that'll be an interesting thing to consider. Combining the dynamic actor garbage collection with static analysis. So in particular, that Fibonacci actor benchmark was a very easy one to manually garbage collect, even with static analysis. So it seems like if we have even these worst case scenarios, maybe we can have a static analysis that removes some of the burden on the dynamic actor garbage collector to improve performance even further. And lastly, would be to see how this scales to large clusters. I've only tested this on small clusters of 3 nodes. So to see how this broadcasting, for example, we have this broadcasting of ingress actor snapshots and delta graphs, right? We can use something like Gossip in order to do that broadcast, but it'll be interesting to see how it scales to hundreds or thousands of nodes, or whatever Akka is capable of scaling to. We'd like to scale with that too. And that's all. Thanks for the talk. I'm open to questions. Thank you, Tanyan.
Yeah.
So one question, if you don't mind. So it seems like you define the garbage collection to only be about idle actors here.
Yes.
But wouldn't it make sense to extend also to busy actors? I mean, if you do something like what Gul does in the Foundations paper, right? You sort of say that you have an actor configuration, and this configuration can receive certain messages and can send certain messages, right? So then we would say that, okay, we can remove a busy actor if it can't affect the messages we are going to send, right? So you have a kind of an observational theory that allows you to throw out busy actors.
Mm-hmm. Yeah, and some prior work has done that. The problem is that the collage-based approach doesn't immediately apply to busy actors. Because if you remember that proof, we carefully relied on the assumption that these actors remained idle after taking a snapshot. And if you start to deal with busy actors, the message counts are no longer necessarily sufficient, I believe. And in addition, you're not necessarily ever guaranteed to get you're not necessarily ever guaranteed to detect that. Well, think about this. If your actors are passing messages back and forth and you get these uncoordinated snapshots, you're never guaranteed to ever get a consistent set of snapshots. They may be garbage because they're busy, but you might never get a consistent snapshot to tell whether they are safe to garbage collect or not. So you'd need to combine this collage-based approach with some kind of more snapshot-based approach in order to collect those kinds of garbage. So that would be a very interesting extension beyond this to deal with those busy actors. But I think it's not immediately within the range of collage-based approach.
Okay, thank you.
Yeah.
But one thing you can do is the receptionists are like your question mark actors, in the sense that you don't know what the information is that is outside. And so if you just assume the receptionist cannot be garbage collected, then the rest of the thing just follows. So as far as dealing with open systems goes, at least in terms of the busy actors, you can do that.
Oh, but I actually do address that in the thesis, where you're talking about actors that can receive messages from the outside world.
Right.
I think what you're
about that. And,
But I think when you're talking about receptionists, you mean actually actors that can send messages to the outside world.
as well,
So,
yeah. There's two things. There's messages that can come from the outside and messages that you can send outside.
Mm-hmm.
And both of those. But messages that can be sent outside is easy to deal with because it's a busy actor and you're not collecting busy actors. You know?
Mm-hmm.
But the
Yeah,
receptionists that can get messages from the outside are like your question marks. You just never collect them.
Well,
And, you know, anybody they know or anybody who can send them the message, you know, you collect them.
Yeah, those particular actors that can receive messages from outside the system, I do address that in the thesis, and those are the sticky actors.
Right. Exactly.
And yeah. So that's the thing. And I would mention that what's interesting about what Carl and Gul are talking about is, for example, Hadoop has this notion of speculative execution, where it sends an actor over here to do a task and it sends an actor over here to do a task. And whichever one finishes first, that's great. The other one needs to be garbage collected because it's doing work, but it's never going to do work that's going to be useful to me. But the problem is, because that's a busy actor, my approach doesn't ever garbage collect that approach, that particular kind of garbage. So you'd need some kind of extension, maybe what Gul was talking about, in order to detect that kind of garbage. That's an interesting extension that I'd very much like to see in future.
This is very good work, Dan. I think you have thought about many different dimensions and aspects of the problem. One question I wanted to ask, I'm still a bit unclear on, is the message overhead, which I think is one of the two big differences between your work and the previous work, the other being fault tolerance. For message overhead, in the evaluation, I was hoping you might have some bandwidth measurement numbers, but I guess you just measured the completion time. Can you again briefly summarize why the number of messages is smaller in your case compared to the previous generations? And I guess I'm also curious about whether the number of bytes going over the network is actually smaller in your case or not compared to the previous work.
Are you talking about Pony specifically, the Pony algorithm? Or
Pony.
So Pony has only been, actually they have done a distributed extension where they ensured that it had the causal message delivery. I think, let me think about the number of bytes shouldn't, we will have, this is a very interesting question. And number one, you mentioned those benchmarks. The Savina benchmarks, they're all single machine benchmarks. So I can't measure bandwidth in that case. And the random workers benchmark, if I don't have garbage collection enabled, the system crashes eventually because it produces too many garbage. So it's hard to do the empirical measurement of that bandwidth. And in terms of, I'm not sure about how much message overhead there would be. The overhead of my approach in terms of messages between nodes, in terms of bandwidth, is those delta graphs that are being sent out. And it's interesting because we have a little bit of a trade-off between how frequently you send the delta graphs and what their size is. If you reduce the frequency, you can have them the delta graphs be packed more efficiently, and that would use less bandwidth. That's one interesting aspect of it. You were talking, but getting back to your question in more detail, you're talking about the overhead of the approach in terms of the number of messages.
Yeah, either number or bandwidth. I mean, I think one one experiment you could do and draw a plot is y-axis is bandwidth, x-axis is, I don't know, maybe different types of applications, and you measure for, in some cases where the delta graphs are more compact, you expect to have lower bandwidth. In other cases where the delta graphs are less compact, you expect to have more bandwidth. So some characterization of the actual network bandwidth would be useful.
Mm-hmm. Interesting. Yeah, I'll think about that, definitely.
So, you can also do a message count for these benchmarks. If you have causal delivery, conceptually you can sort of imagine them on different nodes, and you have causal delivery, there's an extra overhead. And you might be able to do a pencil and paper calculation on the overhead and then compare it to the number of messages that you don't need to send, because your messages are just related to the GC.
Yeah.
Mm-hmm. Since they're not benchmarks, I think you can analyze them.
So just curious, like, let's say like in a typical deployment of an actor system, let's say like an array, you mentioned like array actually using the actor model. So how many actors like are there in a typical kind of array job? So it's kind of in the scale of like thousands or like hundreds of thousands or things like that.
I am actually not too familiar with the kinds of workloads Array does. I know that they were doing some reinforcement learning, and then in that case, I thought that they do like a very few, like you count on one hand how many actors they use in that particular case. Whereas in Akka and Erlang deployments, actors are designed to be extremely lightweight so that you can have hundreds of thousands of actors on a node or spread across multiple nodes. Basically, whenever you want to do a little task, you'll spawn an actor. It's extremely cheap.
But so you do. Facebook chat was done in actors, and they had 200 million.
200 million?
Yeah.
Okay.
So it just depends on the scale, right? So you can get it to.
Yeah.
And Erlang, they were talking about 8-10 million. I don't know if Philippe is.
Yeah, I don't recall exact numbers, but yeah, I mean, Twitter also was using actors, and they also had tens and probably hundreds of millions of actors for manage the client connections and everything. So.
And I would say that this approach is not just useful when you're dealing with lots and lots of actors, because if you consider, for example, Hadoop, you had basically one actor per node or a small number of actors per node. And the key was, though, that you wanted to be able to, like, an actor would represent an entire container, and you want to make sure that those containers are used efficiently. And you want to reclaim those containers when a fault happens, when something